Welcome to this video on our next topic, that is torsion or torsional shear stress. You've actually viewed a briefer on this topic through a called video from the net sources. So today we are going to have examples. So let us start by defining what's the meaning of the torque. So torque is a twisting moment caused by twisting forces in a steel shaft. Basically, if we have here a shaft subjected to a torsion, of course the effect of that would be the twisting on the shaft, creating an angular displacement at the center of the shaft, causing a torsional stress that is brought by this T. So this T has a unit of Newton meter, or it could be pounds foot. So basically, if the force is on the parallel axis of the member, and we have a rotation on the parallel axis, therefore it is torsional stress. So we have here some definitions and notations on torsional shear stress. Torsional shear stress is denoted by just the same. We have tau, and tau is equivalent to T R all over J. T here is the torsion or the torque in Newton meter or pounds per foot. R here is the radius of the diameter of the shaft, and J here is the polar moment of inertia. So J is actually the sum of the moment of inertia along X and along Y. And our focus is on circular shaft, where pi over 32 d raised to 4 for solid shaft, and pi all over 32 d raised to 4 minus the diameter, inside diameter raised to 4 for hollow shaft. So if there is a torsional shear stress on torsional stress, we also have a torsional shear strain. That is simply analogous to what we have discussed on axial deformation, wherein we have stress, simple stress, and simple strain. So this time, we also have torsional shear strain as well as torsional shear stress. So for torsional shear strain, it is denoted by the uppercase gamma. So similarly, torsional shear strain is also deformation. So here we have a subscript S, that is to indicate that this deformation is a shearing deformation. Then all over length. Further, so remember that this deformation is associated with an angle. So the formula of the torsional shear strain expands to writing the shearing deformation in terms of radius times the angle of twist. Then we just copy the divisor length. Synonymous also to the axial deformation for the proportional limit that is elastic, or what we call the Young's modulus of elasticity for axial deformation. There is also a corresponding modulus of rigidity for a certain shear stress. So E for axial deformation and G for shearing deformation. So expanding this G into the formula, similar to E, we have G is equal to shear stress all over shear strain. Then we start to expand the shearing stress and the shearing strain. So this is supposed to be equal to TR over J for the shearing stress. Expanding further the equation, we have replaced that by R theta all over L. So all of these are equal to G. So by expansion, we have GR theta all over L cross multiplying G times this expression. And what is left? TR all over J. Solving for the angle of twist, we have TL all over JG. So theta here is the angle of twist and the resulting unit will be in radians. So these are the principle or basic principles that we need to know regarding the torsional shear stress. To have a recap, we have torsional shear stress tau is equal to TR over J. By the way, the unit here is megapascals. And then J is the polar moment of inertia. And normally that is expressed into the sum of the moment of inertia along X and along Y. Or in short, this is the inertia along Z axis, or this is IZ. So it is just the sum of IX and IY. But most of the problems on a shaft is a circular one, so we're going to have the formula J is equal to pi all over 2 d raised to 4 for a solid shaft, and J is equal to pi all over 32 d4 minus d4 for the hollow shaft. So in short, we're just deducting the diameter or the outer diameter to that of the inner diameter and then raise it to 4 for each. Okay, so next we have torsional shear strain. So similar to the axial deformation, that it has a strain, and just the same, the strain is the deformation all over L, all over the length, but this time it involves an angular deformation, so that is denoted or subscript by S there. And then this delta or the deformation, shearing deformation, could be expanded to the formula, the radius times the angle of twist all over the length. And then analogous, when we have a Hooke's law for E, that is for axial deformation, simply states that the shearing stress is directly proportional to the shearing strain for modulus of rigidity. So expanding further the formula, we will come up with this formula that the angle of twist, that is equal to TL over JG, in which this is the equation that would be most utilized in some problems aside from the shearing stress and the shearing strain. So in order to come up with a simplified solution in torsion, of course we would like to have a technique in order to come up with a simplified solution. I'll just brief you with a simple example or exercises before we are going to have a detailed solution for each of the problem. If we have here a shaft restrained at one end and subjected to several torsion, say 160 Newton meter. Of course, we would like to know the distances. Say we have here distances of 1 meter for the meantime. Okay. We also need to label all the segments here, A, B, and C. So as the first step, we are going to convert the drawing, where if we have a clockwise rotation, we're going to indicate that by a double arrowhead towards right. And if we have a counterclockwise, we indicate that by a double arrowhead towards left. So applying this rule, we have double arrowhead on B, that is equal to 100, and double arrowhead towards left at C, which is equal to 60, and we determine the direction at A. So basically, if we compare 160, 100 is greater than, that is towards right, and this is towards left, we determine which among the torsion will prevail. And obviously, the torsion that will prevail here is 100. So therefore, your 60 will be needing here an additional leftward force equivalent to 40. So it is just converting this into horizontal lines and then apply summation forces or just balance the axis where the arrowhead is, or the axis of the arrowhead. So like this one, we are in equilibrium, so therefore the restraining force to counter this 160 is on the restraining support here at A. So applying that, of course, again we compare 160, 100 is greater than, and that will be towards the right, so that your resisting force should be equal to a 40 that is towards left. By that, we can now proceed to the second step. Step 2, we write the rotation equation. So writing the rotation equation is simply from left to right. So we will just have to refer to this A, B, and C, so that if we are concerned with the whole rotation of the entire shaft, then we are referring to theta AC. And this shall be equated to the sum of the angle of twist at AB and the segment BC. So proceeding to the third step, we are going to solve for the torque per segment. How to do that? By method of sections. All we have to do is to consider some sections per segment. Section AA for the segment AB and section BB for segment BC. If you notice, my section line refers only to a single side, okay? This section BB could always be assumed by you, okay? So it is depending on the student to assume whether you will consider the left or the right portion. But in most cases, it is important, or it is advantageous to direct your section only along one side. Actually, it will be depending on the problem, wherein you will explore it later on. So warming up with this section method, we consider section AA on the left side. We have this as our cut section. And then from our previous solutions regarding the method of sections, we always assume the direction for the torque or the force along this segment. And this segment is actually segment AB, so that the torque here would be segment AB. So instead of assuming a direction, let us all assume that our direction for the torsion is towards right. So never assume a torsion that is towards left. Just always assume that your torsion is towards right no matter what. So what is important, we are starting from left to right, and then on whatever segment we are going to assume a right direction for the torsion. So by that, we have PAB here towards right, and then we apply equilibrium along its axis. This time this is axis X. Then we have this equation. So this is supposed to be a positive 40. So what do we mean if we have a positive answer? Therefore, our assumption that PAB is a rightward force is correct. So again, we are going to assume that the force here or the unknown force will always be towards right, and then your equation will just tell you whether your assumption is correct or not. Just reflect the negative if there is a wrong assumption. As for the section at BB, we have actually the segment BC. So we do consider the forces or the torsion from left of the section and then reflect it by the direction. So 40 has a leftwards and 100 has a rightward, and then this will be the cut section. And thereby this is PBC. Again, this is assumed to be rightwards. Writing now the equation, we have summation forces x is equal to 0. Leftwards 40 denoted by negative. Rightwards 100 denoted by positive. The rightward force for PBC, and this is equal to 0. So solving for PBC, we have negative 60. So negative 60, or the negative sign here, simply means that we have a wrong assumption. But don't worry, because this type of solution will make an easier interpretation for us. Just stick to this negative sign and then do not change the direction of what you have assumed. So as we can see, it is really that the PBC should be on the leftward direction, because 100 here prevails from 40, and that is a rightward force. Therefore, it will be needing a leftward force to counter 100 here and supplement 40, and that is 60. So anyway, there is no problem if we have a wrong assumption. Just stick to this rule, and later on you will discover why is it that this is the pattern of solution. And to tell you the main reason why, because in this case we already know the force here, or the torsion at the leftmost portion, or actually this is a reaction torque on the support. But if this is not given, therefore we will be having a difficulty on what really be is the direction of our torsion per segment. So to make this easier, we will just have to assume that all the unknown torque per segment is towards right, and then let the equation tells us. Okay, let the equation tells us whether we have a wrong assumption or a correct assumption. So what is important, we consistently assume a rightwards. So it could be that if this is not given, once this torsion here like 40 is not given, and then we assume it to be a rightwards for the first segment, and then you are going to assume it a leftward for the second segment, then we will be having a trouble on our equation. Okay, so it will yield to a mistake. Okay, so this is the approach in obtaining the torsion for each segment. And for the last step, of course, we are going to go back to our equation. We just expand this to its formula, that is the angle of twist is equal to TL over JG. So depending on the unknown in the problem, these are the steps in solving problems in the torsion. So for this particular example, only one of the end is restrained So in particular, this is restrained at the left portion. But what if the shaft is being restrained at both ends? Say for example, we have another shaft here, restrained to both ends, having several segments. So the ends are restrained. So we have the same procedure. We are going to follow the step-by-step procedure, but on on the second step, on writing the angle of twist, let us have a condition where the both ends are restrained by the wall. So the meaning of this is that both ends will have no rotation because it is being restrained, or it is rigidly fastened on A and E. Therefore, theta A to E is equal to 0. So this will be our working equation for the angle of twist from A to E. So then we can expand theta A to E to the sum of the angle of twist per segment, theta AB plus theta BC plus theta CD plus theta DE. So if we're concerned from A to E, that is equal to 0. However, if we are concerned with A to D, there will be a rotation in it. So let us practice that one. We have theta AD is equal to theta AB plus theta BC plus theta CD, and we do not need to add theta DE. Similarly, if we are concerned with theta A to C, we have theta AB plus theta BC. So if you would ask, what if we have theta AB? Theta AB is actually the angle of twist at A support. Okay, because if we're going to have a section here, okay, that is, we have here torque at A, and this is torque at AB. So therefore, theta AB is equal to theta A. So that's it for the step-by-step procedure. And if you know these procedures, then you will not be lost on whatever problems on the our topic, okay, or even in board exam. If you know this procedure or the step-by-step procedure, you will not get lost, okay. Of course, on the condition that you are familiar with the units as well as the formulas that was introduced a while ago. So later on, this is expanded into the power that is transmitted by the shaft. But for the meantime, I will not, I would not like to bombard you with a lot of formulas because you might get lost. Okay, so for the meantime, we are going to do this gradually or little by little. Okay, so thank you, and at your home, you may practice problems using the principle I have shared with you, and I think this is the best way how to solve problems in torsion. So just follow the step 1, convert the drawing. Whenever we have a clockwise, just indicate that into a double rightward arrow, and if we have a counterclockwise, indicate that with a leftward arrow double head. Okay, so as a second step, we have write the rotation equation. Of course, it is so easy to write the rotation equation. We'll just have to sum up the letters here. So if we have AC, it is just AB and BC. And if we have AE, that is AB, BC, CD, and DE. If we have AD, that is AB, BC, and CD. If we have AC, AB plus BC. And then AB is the edge, of course, the nearest uh, location is A, therefore that is theta A. So the key here is that you start writing the angle of tilt from left to right. So that is very important to note. And then for the step 3, solve for the torque per segment. You have already done this a lot of times during your engineering mechanics. Just have a section wherein the section could be assumed or cut considering only one direction. Okay, but my advice is if you are going to have or a multiple section here per segment, you'll just choose left or right. Okay, so usually or normally if we start our work from left to right, we always direct our cut section and consider the left portion because we are always starting with the left portion, so we always cut the section and then consider the left portion of the shaft. And the third step, the step 4, and we are going to expand now what we have written on step 2 and solve for the unknown. So thank you and have more practice at home.